Um, so welcome back, everyone. For our next talk, we have Ben Antieau from Northwestern, who will tell us about binomial rings and stacks and topology.
Okay, thanks. Thanks a lot for the invitation. It's nice to speak in this seminar. So today I want to talk about some work around the following question, which is rather classical. So let's let K be a commutative ring and X a space, or anima specifically. Then the question is, to what extent can we recover X from the ring which computes the cohomology of X? So I'll write K upper X, and if you like, this is what you might also write as chains, cochains on X with coefficients in K. And here we really are wanting to view this as like, you know, an E infinity ring or something else. Some kind of highly structured object. And the basic idea is, well, there's a whole history of recovering the homotopy type of X from various algebraic objects attached to it. And you know that you can't do it if you just remember, say, the cohomology ring. There are lots of spaces with sort of the same graded cohomology ring. And so we sort of impose more and remember more and more structure to try to get closer and closer to the homotopy type of X. And the first thing to say off the bat is that no matter what you do, you're not always going to succeed. Not always possible. There are acyclic spaces. There are spaces X such that even the integral cochains are just equivalent to Z, but where, for example, pi1x is not 0. So these are acyclic spaces. And for example, Dror in 1972 showed that they exist with any pi1 which is super perfect. So for any group which is super perfect, meaning that H1 B pi1 Z and H2 B pi1 Z both vanish. So for any group which satisfies these conditions in its group homology, then there are spaces with that pi1, but which are acyclic, for example. And so you're never going to recover these spaces from their cohomology ring, obviously, because it just looks like a point. So instead, or another example, you could sort of take Q cochains, but of a space like K Z mod Pn. And this would also be equivalent to Q for n at least 1. Okay, so there's also an interaction between the sort of homotopy groups and the nature of the homotopy groups in the space and the ring that you're taking coefficients of. Okay, so if you take them so that they don't talk to each other, then you're also not going to be able to recover what you want. So as a consequence, one typically imposes some extra conditions on the space. One pretty standard thing to do is to talk about nilpotent spaces. So I'll write S nil for the full subcategory of spaces which are nilpotent. And what I mean by that is that each pi1 of X, So X is in here if each pi1 of X is a nilpotent group. Meaning at each chosen base point. So I'm not assuming that it's a connected path connected, but at each base point, pi1 is nilpotent, and X nilpotently on each higher homotopy group. I'm enjoying the historical commentary, but I might not notice it. So please interrupt if there's any questions or comments. This is a category of spaces which in the end is all built up of out of, one way you could say this, it's built out of k pi n's for a abelian pi, and using principal fibrations. Okay. So these are ones which are very, very close to being in the world of well, yeah, built from abelian groups. And I'm gonna have occasion to work with some finite versions of this category. And so let me just say that I mean, this is sort of not really standard notation, but let's say S fin inside S nil. Let me impose here the additional hypotheses that pi 0x is finite. And X is truncated. So zero for I sufficient at all, and since pi 0x is finite, then there's in fact a uniform bound that works on each component. And let me just say just a little bit more. I'm going to have occasion to talk about 3 additional special subcategories here. So these will basically be finite nilpotent spaces, which are additionally built out of sort of finitely many copies of Q. So I'll just say this is finitely many copies of KQNs. This is sort of finitely many copies of KZNs, or sort of KZ mod, I don't know, MNs. And this is finitely many copies of KZ mod PN for a fixed prime P. And when I say finitely many copies, I mean, for example, that the fundamental group, it's nilpotent, and I'm saying in the P finite case, it's just a finite P group. Okay, and the higher homotopy groups are then also just finite, they're finite abelian P groups. Similarly, in the rational case, I'm saying that pi1, it's a nilpotent group, and in its whatever lower central series, each of the graded pieces is a Q factor space. And there's only finitely many, and similarly, the higher homotopy groups are finite dimensional Q factor spaces and so forth. So it's just some finiteness hypothesis I want to keep in mind. And let me tell you 2 of the sort of classical theorems on this. And now that I've introduced this notation, maybe I'll pause and see if there are any questions. I have one more definition I want to give. So suppose K is a commutative ring. And let me assume it has no idempotence besides 0 or 1. or equivalently that spec K is connected. I'm going to introduce a space, not written this way. A subcategory of the category of commutative K algebras. So these are just discrete K algebras, and I'm going to call these stone K algebras. So this is just the subcategory generated under colimits by the objects K upper S, where S is a finite set. So you just look at all finite products of K as a K algebra. Okay, those are not the most interesting K algebras. Geometrically, it's just like finitely many points. But they're each finitely presented as K algebras. And the class of these is also closed under tensor products and retracts. So retracts by this condition on the idempotence and tensor products, I'll leave it for you to check that KS tensor KT is isomorphic to KS cross T. And that means that if I close this up, I get a presentable subcategory, which is closed under colimits in the category of all commutative rings. Okay. So we're going to meet these in different guises, but it's one way I'm going to state a couple theorems. So, okay, what are these two classical theorems? So the first one is due to Sullivan. And it basically gives the rational case. So I'll say it like this. So I have a functor, contravariant functor to, I'll just write this, delg Q CoKonnective. These are sort of derived commutative Q algebras, or you could say E infinity Q algebras, which are CoKonnective, meaning that HI of R is 0 for I less than 0, for CoKonnective, I more than 0. And you can model this particular thing by taking CDGAs over Q and inverting the weak equivalences, and then looking at the CoKonnective ones. So that's one concrete model for this. And I have the cochain functor, which takes Q finite space to Q upper X, the thing which computes the rational cohomology of X.
Excuse me, do you mean that HI of R is 0 for I larger than some finite number, or really just for all positive I?
I mean for all positive I.
So does that mean there's only an H0? Or is there negative?
It can have negative. It can have negative.
Okay.
Maybe we're doing cohomology, so I could write HIR is 0 for I less than 0.
Okay. Okay.
Just the cohomology of a space doesn't have negative cohomology.
All right. Thank you.
So this is a functor, and the claim is that it extends to a fully faithful functor. From the category of pro-Q finite spaces up into the same target category, delg Q CoKonnective. And the essential image is is inside sort of delg Q CoKonnective stone, i.e. those are where additionally H0R is a stone Q algebra. Okay, so I'm saying two things. I'm saying that this functor is fully faithful, and I'm also restricting the target, the place where it can land, and I'm saying that it's landing in sort of CDGAs or E infinity Q algebras, where additionally the degree 0 cohomology ring stone. And okay, I mean, this isn't exactly how Sullivan would have phrased it, but it's okay, so that's theorem one in this classical direction. And so this is great. This is telling us that for a large array of spaces, we can recover the space in some sense from its cochain ring. For example, the way that you would recover the space itself is you would take the mapping space in this category, dalg Q coconnective, from Q cochains on X back to Q. And by fully faithfulness, that's the same as maps. This is Q upper a point, right? The Q cochains on a point. So this is maps from point to X in spaces, which is equivalent to X. And then it extends to some category of pro spaces as well. And the extension to pro is nice because that includes taking the Postnikov tower. And so you get also finite type, you get unbounded spaces from this picture as well. Okay, so this is a sense, and if you think about it, this is kind of like the space of augmentations of your algebra, and we're saying the sort of space of augmentations of Q cochains on X is X. That's one way of thinking about this theorem. So this is quite classical. And now another theorem is much more recent. And that's due to Mike Mandel. And it says if you do sort of P finites, or maybe even P finite type spaces, op into E infinity FP bar algebras, sending X to FP bar cochains on X. And here P finite type, this is inside pro P finite spaces. And it's just sort of saying that it's going to be some special inverse systems. It's not going to matter that much for us. But anyway, so this thing which takes FP bar cochains on a P finite or a P finite type space is fully faithful. And so again, we can recover the X from its maps to FP bar, maps of its FP bar cochains to FP bar. Okay. Let me just remark that there's also versions of this where instead of working with cochains, you work with chains. And then you look at either a coalgebra structure or some kind of Lie algebra structure. And that was studied by, that's been studied by various people, but especially Quillen. Also, Paul Gorse has some work in the p-adic case. And when you do that, because you're not by taking cohomology, you're sort of dualizing. And that's where these sort of finiteness and pro stuff, where that comes from. And you can get away from that by doing the chain version, but at the cost of working with like objects that I would say that we're on average less familiar with, coalgebras or things like that. Whereas it's kind of very nice to think about algebras. Okay, so that's the background and history. Let me pause and see if there are any questions.
Yeah, Ben, I think that very recently there was a preprint by Bachman and Birkeland.
Yes.
That addressed something related.
Yes.
To this as well.
Yes.
How does that fit into this sort of historical picture?
That's also on the chain level, and it's related to Paul Gorse's work. Yeah. have to say I didn't take a super close look at it. So any other questions? So if not, then the goal today is to talk about some sort of integral construction. And this is really a, here we can sort of, if you take a general space, like what you're sort of saying is that for a general space, X general, then, if it has some reasonable finiteness properties, then the Q cochain algebra should remember the Q localization of X, or the Q completion of X. And here, down here in the Mendel sense, FP bar cohomology of X should remember the p-adic completion of X in the sense of Busfield and Kahn or something. And of course, we don't want to just remember the rational or the p-adic homotopy type. We would be interested in recovering the full integral homotopy type. And this is a problem that if in some guys, even Grothendieck considered various versions of this in his Pursuing Stacks project. And it's also been something that Bertrand Tohen has studied quite a bit over the years. And also Mike Mendel has some results on this in his IHES paper, where he shows that the integral, if the integral two integral cochain algebras are equivalent, then the spaces are equivalent under some nilpotence conditions. But he doesn't get a fully faithfulness result. Okay, so it's some kind of conservativity result, but not a fully faithfulness result. And so it's sort of a problem to construct an integral version of this. And one thing we would like to do is to use the following thing proved by Sullivan, which is that we can recover a space, oops, I'm sorry about that. We can recover a space X from, there's some kind of arithmetic fracture square. I can take the product of the p-completions, and then rationalize, and I can also rationalize. And there's a canonical commutative diagram, which is a pullback diagram for X inside. So this is also due to Sullivan, and for a nilpotent space. I get a pullback diagram like this. So we can recover a space from its sort of p-adic and rational completions and the way that they glue together, just like we can do so for an abelian group, or for a complex of abelian groups, or for a spectrum. So there's some kind of the version of this for topological spaces, which is well known. And what we've just said is, by using FP bar cochains on one hand or rational cochains on the other, we can kind of recover these vertices of this square. And so now, of course, we'd like to be able to glue the rest of the square, but now the problem is what we're using here might be rational chains. And what we're using here might be, if I just focus on one prime, FP bar chains. There's no way to glue these, right? FP bar chains, if I rationalize, I definitely get 0. So there's going to be some subtlety in gluing these together effectively. And so I'm going to tell you about a version of this theorem of Mendel, which will allow us to make an integral lift of it, a p-adic integral lift of it, that we can then try to glue together. Before I do that, I wanted to give just, I'm not going to give a full proof of Sullivan's theorem, but I wanted to mention, so you get a taste of what's involved, like what the crucial piece of information is needed to prove it. So first, basically, you just do some easy category theory, make some argument with limits and colimits to reduce to checking that that maps from a, so you get down to a single Eilenberg-MacLane space. So Q cochains on KQN back to Q is equivalent to K QN. So, and this is sort of easy. I mean, you kind of use limits and co-limits to get rid of the pro systems, and then you also use that this variable it takes co-limits in a space to limits, and so you can write a space as a geometric realization of a bunch of points, and then you can also get rid of that, and so you reduce to the case where this target is just you're really just doing it for maps from a point to X, and then you use the Postnikov tower and Eilenberg-Moore to reduce to a single Eilenberg-MacLane space, and now we have to check it for that. But now this is super classical, and it's easy to compute that this is the free Q algebra, sort of derived commutative Q algebra on a degree minus n generator. So, for example, for n equals 1, that's just saying that the free algebra on a degree minus 1 generator, that's an exterior algebra since we're working over Q, and that's giving us the cohomology of S1. And then it follows in general by taking a bunch of bar constructions. And of course, now, since I know this, I know how to map out of a free algebra, right? Mapping out of a free algebra, this is just maps. So this is maps in sort of derived commutative rings, but I'm mapping out of the free algebra. So this is just maps in Q modules from Q minus n to Q, and that is this Eilenberg-MacLane space. So, okay. So that's the fundamental thing we need to do to prove each of these various types of theorems. In the end, it's going to come down to analyzing, what is the cohomology of an Eilenberg-MacLane space as an object in our category of commutative rings. And John gave a timely remark about Boolean rings in the chat, and we're going to go towards those now. So now let me talk about what we're going to do p-adically. So okay, so inside commutative FP algebras, each FP algebra has a Frobenius given by phi x equals x to the p, and I can look at the perfect ones. So this is just phi as an iso. The commutative FP algebras where phi is an iso. This functor has both adjoints. The left adjoint is given by the colimit perfection. So R, R, R. And there's also a limit perfection. You take the inverse limit of along Frobenius and you'll get a perfect ring. And now I'm going to talk about a subcategory of this, calg FP phi equals 1, where in fact you ask for x for phi to be equal to the identity. In other words, x to the p equals x for all x in your commutative ring. And I'll call these p-Boolean rings. P-Boolean, because for p equals 2, these are classical Boolean rings that come up in various places. And this also preserves, this also has both adjoints. I can take so the right adjoint, this is just sort of X in R such that X to the P is equal to X. That's a subring. And the right adjoint, this is the co-equalizer in commutative rings of the two maps. Identity and phi from R2 itself. Okay. And just as a, an important fact is that this is actually equivalent to what I introduced earlier. These are the Stone FP algebras. Precisely the things built out of, under colimits out of finite products of FP itself. And that turns out to be the end category of the opposite of finite spaces. And the correspondence, well, let me tell you that this is also the same as pro-finite op. So this is the opposite of the category of profinite spaces. And this is something called Stone duality. It says that a profinite space is captured by the ring of, so this map sends a profinite space S to continuous functions from S to FP. That's a totally nice commutative ring, and the Frobenius on that ring is the identity. And then this map takes spec. And those are inverse equivalences. And so the reason that I brought up Stone earlier is that I want to view this as the degree 0 case, or the zero truncated case of the sort of theorems that we're looking for. So I want to view the Stone duality as an example of recovering a space from its cochain algebra. In this case, the cochain algebra happens to be an ordinary commutative ring. But we want to build a theory that kind of does both at one time, and I find it helpful to think of this way. Fun fact, you'll notice that there's no P on this side, which means that these categories are all equivalent as categories as P varies, but they're not equivalent as concrete categories. Like they don't commute with the forgetful functor to sets. So anyways, I found that to be amusing. Okay. So to say what we're going to do next is we're going to build a derived version of this whole story. So there's something called I probably won't say much about this, but there's something called derived commutative rings. So this is basically built as follows. You take the monad given by animated commutative rings, or simplicial. So this gives you an L-sim monad. And you just observe that this extends to a monad on the full derived category of the integers. And by you, I really mean this is due to, Akil Matthew, maybe Lucas Brandner, and Arpan Roxet. And so it extends to some monad, and you just declare a derived commutative ring to be an algebra for that monad. And the important thing is that the forgetful functor to E infinity algebras over Z preserves all limits and colimits. So an example is Z cochains on a space. This is really limit over the constant diagram on X of Z. Z is a derived commutative ring. And so this limit comes with a canonical derived commutative ring structure. The same would be true for cohomology of a topos with coefficients in a sheaf of commutative rings. So there's something called these derived commutative rings. I'm going to use these. There's also, of course, there's derived commutative FP algebras. And my student Holman constructed Frobenius on these. So if R is in here, then it has a Frobenius endomorphism. There's a couple, yeah. In the case of connective, this is very easy to see. You model it by a simplicial commutative FP algebra and just apply the Frobenius in each degree. It's a little bit harder to do in this case. But I can, right, and then I can look at the perfect ones, which are just the ones where the Frobenius is an equivalence. And on this category, this Frobenius really corresponds to an S1 action. It's a natural it's giving us a natural isomorphism of the identity functor. And so I'm going to let my p Boolean derived FP algebras has a forgetful functor to this. This is going to be defined to be the homotopy fixed points of this S1 action. So it's the structure of derived commutative FP algebra where the Frobenius is an equivalence and where you've also kind of in a coherent way trivialized the Frobenius. Okay, so this is now saying that the Frobenius is actually equivalent to the identity. And these are going to be my p Boolean derived commutative. And so this is just some algebraic category. Let me just note that a priori objects here have higher homotopy, typically. But any perfect one implies that the higher homology groups are 0. Or higher homotopy groups, whatever. Just turns out that Frobenius acts nilpotently on the higher homotopy groups of a derived commutative FP algebra, so that when you perfect, everything goes away. That has a kind of curious. Okay, this is kind of irrelevant, but I think this fact is cute. So sort of if you take perfect FP algebras and you animate this category, so that by which I mean this has some compact projective generators given by tensor products, finite tensor products of this basic one. It's the perfection of it's the perfect polynomial ring on one generator. And so you can use the usual animation trick, basically given by simplicial commutative perfect polynomial rings. And it just turns out that this animated category is not a higher category. It's commutative FP. It's perfect commutative FP algebras. So somehow there's no higher structure when you do this animation. I actually don't know of another natural case where this happens, where the animation of something, it turns out to be a one category. I mean, in some for some non-trivial reason. Okay, so what's the theorem about these? So this is due in some form to Igor Krish, and then in the form I'm giving here to myself. And it's some kind of like push out of Mendel's theorem and stone duality that captures both at the same time. And so the functor is that the statement is that if you take FP cochains on a p finite space, well, FP is in particular p Boolean, and so you're taking a limit of p Boolean rings. And so that naturally has its own p Boolean structure. So you land in here. So sending x to FP cochains on x. This extends to an equivalence from pro p fin op to delge FP phi equals 1. So in this case, we get an equivalence of the entire categories, which is remarkable. From a certain perspective, if you work with simplicial and cosimplicial objects, this can be viewed as almost tautological, except you have to contend with what the right notion of equivalence is. And it's maybe a little tricky to see that, and to see that as sort of equivalent to the proof that I'm going to give. So, and that's what Creech did. And okay, maybe I'm not going to sketch the proof, but maybe maybe let me just remark what you prove is that FP. You prove again that this FP cochains on KFPN for n at least 1, that this is the free p-Boolean derived commutative ring on a degree minus n generator. And to do this, the proof I have uses higher stacks and Toen's theorem about them. So, okay, I don't really have time to say much more about that proof, but it's, in the end, you have to check something like that, and you do. Now, let me rapidly say, still, I said we were going to do something integrally, but I'm still stuck in characteristic P. But now is where we can use, my idea was, of course, we understand lifts of characteristic P rings to characteristic 0 via delta rings. And so FP to ZP, let's say. So I want to now take do FP coefficients to ZP coefficients. And I'm just going to assume that you understand and know what delta rings are. If not, then we can talk about that afterwards. And so there's a category of derived commutative delta rings constructed again by my student Adam Holman. Delge. The animated case was considered in Bott and Lurie, I suppose. So there's some category of derived commutative delta rings, and a theorem about these is the following: whatever these are, they're built out of delta rings. So there's a forgetful functor which has both adjoints. The left adjoint is the free thing, and the right adjoint is given by some derived version of Witt vectors. But the theorem is, first of all, that if you look at the perfect delta ring, so every delta ring has an associated lift of Frobenius. If you look at the perfect delta rings, which means that this lift of Frobenius is an equivalence, and you look at the ones which are also P complete, I'll denote that by this little wedge. This is actually just equivalent to derived commutative FP algebras, which are perfect. And so we also get that delta rings where the Frobenius is the identity, which are P complete, that's equivalent to P Boolean derived commutative rings. And there's a couple other variants, but let me stick with these for the moment. And as a corollary, you get that the map from pro-finite pro-P finite spaces op to delge ZP delta rings where the Frobenius is 1 and P complete, this is an equivalence. And this is now X goes to ZP chains on X, viewed as a derived delta ring. So I'm viewing cohomology now as having a delta ring structure. but where the lift of Frobenius is the identity, is canonically given by the identity. And that's actually an equivalence of categories. Remark, the vid vectors on FPX is equivalent to ZPX if you kind of do all of this stuff in the right way. Okay, my time is up. Let me take 1 minute and just give very briefly what happens integrally. I now want to make some algebraic structure which captures a lift of Frobenius at each prime together with the fact that that Frobenius is the identity. And that was actually just already understood in classical algebra. So lambda rings correspond to compatible lifts of Frobenius, which are the associated Adams operation psi p for all p. And what are called binomial rings in the literature. So these are torsion-free rings R, meaning that R is contained in its rationalization, closed under the operation X maps to X choose N, which is X times X minus 1, X minus N plus 1 over N factorial. So they're torsion-free commutative rings, which, inside the rationalization happen to be closed under this operation. And so lambda rings correspond to these compatible lifts of Frobenius. Binomial rings correspond to psi p equals the identity for all p. And in that case, the binomial rings, this is lambda n x. This is the Adams operation. And if you sort of work out, if you kind of reverse engineer, starting from the fact that you want the Adams operations to be the identity, you get that this has to be the Adams operations by some generating series argument. And so let me just say this, that I build some category of derived commutative lambda rings where psi is equal to 1 for all integers. And then the theorem is that there's a map from spaces into here. Maybe finite type xenopotent spaces op into here is fully faithful. And I should mention that more or less this theorem is also proved by Geoffroy Horel in independent work, and also Kubrak, Shuklin, and Zakharov. We all sort of take different approaches to setting up the machinery, and it's actually a priori a little bit, we haven't been able yet to completely compare the different categories we construct. But okay, I'll stop there. Thank you for listening.